In this video, we'll discuss the normal distribution. The normal distribution is the central distribution to statistics. It's the most important distribution. It allows us to do inference in statistics. Many variables are normal in nature. For a normal distribution, here are the properties. The curve is symmetric and unimodal, which means that your curve looks something like this. Remember, a symmetric distribution is any distribution that has tails on both sides, and the mean is equal to the median. But here the curve is symmetric and it's unimodal. Unimodal meaning one mode. And what this essentially says is that a lot of the values are occurring in this peak area. And as you move away from the peak to the left, the values start to get fewer and fewer. And as you move away from the peak to the right, the values also start to get fewer and fewer. So as you can see in this distribution, very extreme values being way out here or way out here, those are occurring with the fewest amounts here. The next thing is the normal distribution has two parameters. Just like the binomial had two parameters, which were n and p, the normal distribution also has two parameters, which is the mean and the standard deviation. So we have the mean mu and the standard deviation sigma. The mean will always sit at the middle of this curve. It's always in the middle right here. Here is your mu. And every place where the curve is supposed to drop, we call those inflection points. This is an inflection point. Here's an inflection point. And here's an inflection point. Where the curve is supposed to drop towards the x-axis down here, those are going to be standard deviations. So from here to here, for instance, is 1 sigma in both directions. So this is mu plus sigma. This is mu minus sigma. Here is mu minus 2 sigma. Here is mu plus 2 sigma. This is mu plus 3 sigma. This is mu minus 3 sigma. And notice here I only drew 3 sigmas in both directions, 3 standard deviations in both directions. That's because majority from the empirical rule, we should remember that for the majority of our data, it falls within 3 standard deviations of the mean. So every normal curve, most of the data will fall within 6 sigma or 6 standard deviations under the curve. The tails extend in both directions forever and are asymptotic with respect to the x-axis. Well, that means these tails will go forever in this direction, the negative direction, and they'll go forever in the positive direction. They'll never touch this axis, although they'll continue to approach it. And again, that just means we have very few values out here on the left and very few values out here on the right. But because it's asymptotic, it's boundless too. Now, the other part of this is that the area under the curve is 1. And we're going to associate this area with probability. So what's going to start happening now is we're going to start calculating the area underneath the curve up to a point. So for instance, if I calculate up to 1 standard deviation like this, I'm going to calculate the area all the way back here up to this. When you start to calculate area under curves, that is the branch of calculus. So we're going to integrate to get these actual values now. Most people haven't taken a calculus class that takes this course, so integration is going to be hard for you. So we use our calculators to do the integration for us, and we'll get to that later in this video. So let's look at this example. Consider the normal curves A, B, C, and D below. I want to know what is the mean of each curve. Well, we said the mean of the curve sits at the middle of the curve. So we're looking at these curves and we're trying to find the mean. We want to find the middle of each curve. So curve A has a mean that sits at the middle, which is at -2. We'll write it like this: mu of A equals -2. It looks like curve B, C, and D all have the exact same means. They're all sitting at a mean of 0. So we'll write it as mu B equals mu C equals mu D, and they're all equal to 0. What makes B, C, D indifferent though? Well, you can see that B is a much tighter curve than D and C is a much looser curve than B and D. Why is that? Well, that's because their standard deviations are different. So which curve has the smallest standard deviation? And again, standard deviation is the on average deviation away from the mean. So whose values do you think are going to have the smaller standard deviation? When you're talking about smaller standard deviation, you're thinking about tighter curves. Who has the tightest curve? That means you're getting more data underneath the curve in a smaller amount and a smaller distance. And if we look here, look at B. You have to fit a lot more data underneath this curve in a smaller distance. So the standard deviation has to be smaller. So who has the smallest standard deviation? mu of b. Why is it the smallest? It has the tightest curve. Which curve has the largest standard deviation? Well, again, standard deviation, the on average deviation away from the mean. Whose curve is spread out the most? We can see that that is curve D. And why is that again? Mu D is the one that is spread out, or we'll say has the most spread of the curve. Has the, let's call it largest spread. So again, all these curves look exactly the same shape. They're all symmetric and unimodal. The only thing that's different about them is that they have different means where their centers are located at and different standard deviations, how wide and how spread out they are. Let's look at this example. It says estimate the mean and standard deviation from the graph. Well, in order to find the mean, let's start there. To find the mean, we're going to look at where the center of the curve occurs. And so if we draw a line to the center of the curve, it looks like the mean sits at 0. Mu equals 0. The next part says find the standard deviation of the graph. Well, most people are going to assume the standard deviation is 20. But that's not correct. And here's why. Here's what we know about here are the properties that we know about standard deviation for a normal distribution. How many standard deviations have to lie underneath this curve? If you recall earlier in this video, I said that it was 6 standard deviations. Well, to find the standard deviation, all we need to do is this. What is the range from this side all the way to this side? Well, from the middle to the left, from 0 to negative 100 is a range of 100. And then from 0 to a positive 100 is a range of 100. So our total range, or you can do 100 minus a negative 100. We can do the range like this. 100 minus a negative 100. 100 plus 100, that's equal to 200. So the data underneath this curve is falling under a range of 200, and it's spread out over 6 standard deviations. So to find sigma is equal to 200 divided by 6, which is 33.3. So your standard deviations occurring, your first one's here, next one here, and the last one's way out here. Same thing here, first one's here, next one's about here, and the last one's way out there. So the last 2 examples have led us to this thing, then, this problem that persists with normal distributions, is that there's many curves that are normal distributions, or they're normal curves. And it presents the problem when we try to compare things. When we compare, we want to have one distribution that we can compare everything to. And we fix it by using what's called the standard normal, or the z-curve. And the standard normal is a normal distributed curve, is a normal curve. But it's based off of the z-score transformation. And recall that the z-score is the number of standard deviations above or below the mean. We can find it by using this. This is called standardizing. This is called standardizing. When you standardize a variable, it means you use the z-score formula to bring it back to a curve that has a mean of 0, a mu of 0, and a standard deviation of 1. And so what this does is every curve that we have can be standardized by using this transformation right here. And it's going to allow us to compare a lot of curves together. And when we talk about comparing, what we're trying to find now, we're going to try to find the area underneath the curve. And when we find the area underneath the curve, we're going to use this basic rule here to help guide us through this. And we can see that at a standard if a value has a z-score of 0, it sits at the mean. The mean of this curve is 0. If the area underneath the entire curve is 1, the area up to the mean, well, the mean sits in the middle. It means that this area is 50%, which means that if a value falls below the mean, we know the area should be less than 50%. If a value falls above the mean, we know the area should be greater than 50%. That's a general rule we're going to use to help check ourselves. But what we're going to do now is we're going to find z-scores, place them on this curve, and then try to find the percentages or the area associated with them. That area is what we're going to associate a probability with. And here's what we're going to do. For every one of these curves now, we're going to find a z-score. And when we find that z-score, we're going to draw a z-curve. which means the mean of that curve is 0 and standard deviation is 1. We're going to place that z-score on that curve, and we're going to shade these curves depending on what the problem tells us to do. So here's an example. It says the average speed of vehicles traveling on a stretch of highway is 67 miles per hour with a standard deviation of 3.5 miles per hour. Assume speeds are normally distributed. What is the z-score that corresponds to a vehicle with a speed of 70 miles per hour? Use a sketch of a normal curve to find what percentage of vehicles have a speed higher than 70 miles per hour. So the first part of this works like this, and here's what you're always looking for in one of these problems. The first thing you want to identify is somewhere that it tells you that it's normally distributed. Because if it's normally distributed, what that means is we can draw a z-curve. And so the first thing we're going to do is see where it's normally distributed. We're going to draw a curve. And on this curve, we're going to label the mean as, because it's a z-curve, the mean is 0. Standard deviation is 1 to the right, 2, and 3 to the right. There's -1, -2, -3 to the left. Remember, 3 standard deviations to the right, 3 to the left, a total of 6. The next thing we're going to do is we're going to take the information given to us, and they tell us that for this particular curve up here, it's normally distributed with a mean of 67. So we know x follows a normal distribution with a mean of 67 and a standard deviation of 3.5. What I want to do is find the z-score that corresponds to 70 miles per hour. So z is equal to, and again, the z-score formula is z is equal to x minus mu divided by sigma. Well, the x here that I'm asking about is 70 minus the mean, which is 67, divided by 3.5. So we do 70 minus 67 divided by 3.5, and I get 0.857. Now let's talk about the z-score real quick. Notice the z-score is positive. Well, why is it positive? It's positive because the value 70 with respect to the mean 67. 70 is going to lie above the mean. Well, how far above the mean is it? It's 0.857 standard deviations above the mean. So that means it's a little bit less than 1 standard deviation. So here's the z-score for 70 miles per hour. It's 0.857. The next part says use the sketch of a normal curve to find what percentage of vehicles have a speed higher than that. So if we're going to graph this, we would do this. We would draw this, and then we're going to shade this. They want to know higher. Higher means then if you want to go higher, you have to go to the right of this curve. So you would shade this curve to the right, and you want to find this area here. Well, in the next set of videos I'm going to show you how to find this area using your calculator. Because what you have to do now is integrate from this 0.857 all the way up to this value up here.